morning. How's that? Good. All right. Well, again, my name is Glen Leverich. I'm a geomorphologist with Stillwater Sciences. We're a science consulting firm, work all over the West, and more recently working in the Virgin River. So this is a talk that's essentially split into two parts, and it's covering a ecohydrological assessment that we've been applying on the Virgin River to help guide restoration. Being a geomorphologist, my focus is on the physical processes, so that's my first part here. So understanding the hydrogeomorphic processes on the very ecologically sensitive Virgin River. My colleague Bruce Orr, biologist, is going to be covering the biological elements in the next part of the talk. There we go. Excellent. So what's going on the Virgin River? So this assessment is to support a broader restoration framework to specifically address the issues that Tom brought up yesterday with the tamarisk infestation and the recent establishment of the tamarisk leaf beetle. And at the same time, the co-occurrence with the endangered Southwestern Willow Flycatcher habitat. So the need on the Virgin River, which isn't unique, but is definitely a very urgent need of identifying suitable areas for restoration in this ecologically sensitive and very flood-prone, free-flowing river. So how do we identify to achieve cost-effectiveness and restoration long-term sustainability in this entire river corridor, or at least in certain portions of the river corridor? So how do we be strategic about that and factor in the physical and the biological components that we know, and others have already talked about this week, that we know are important when identifying habitat suitability? So this is some of the motivation for the need. These are some photos that Tom Dudley took before and after the recent December 2010 flood of a restoration area in Mesquite. And Bruce and I are going to be using this part of the river as a case study, but we ultimately looked at the entire river. This is the photo on the left is before the 2010 event. You can see the willow plantings in there. And unfortunately, the 2010 flood came through and took out all of that hard earned money and hard spent hours and blood, sweat, and tears. And this is a common occurrence along the entire river. It's not just Mesquite, but also in St. George. So we're talking Utah, a little bit of Arizona, and a lot of Nevada. So we're almost done with our assessment for at least for the first part on the Virgin River, but we've already applied this successfully on a very similar system, and I'm going to quickly walk through these steps to explain this approach. And this was on the Santa Clara River, not in Utah, but in Ventura County, so Southern California, a very similar semi-arid episodic system. Similar invasive plant issues. Here it's arundo, it's not tamarisk so much. So these are the steps outlined that we applied on the Santa Clara. This is work that we did for the California Coastal Conservancy. The first step was historical flood mapping and a more detailed fluvial geomorphic analysis. And the flood mapping essentially was using aerial imagery that was taken shortly after large flood events where there was channel resetting action and delineating those effects, so mapping out where changes actually occurred. The second step was very detailed vegetation mapping, field-based from essentially the entire river valley. And number three was a subset of that, focusing on the invasive species. So there, again, it's a arundo donax. If you're not familiar with that, that's giant cane, which you can see here. It is the blob. It's terrible. Even as a geomorphologist, I don't like it because it actually affects the morphology and morphologic character of the river. Number four is getting more into the vegetation dynamics and the wildlife habitat conditions. So we're talking avian, terrestrial, and aquatic species. Number five is boiling all of that down, synthesizing that to inform on the restoration strategies and management decisions. And then number six came out a arundo strategic plan for control and riparian restoration. Okay, so I'm gonna walk through these steps real quick. And what am I talking about for flood mapping? And I'm talking about geomorphic change. I'm not talking about FEMA or HIC-RAS modeling of where the water went. We're talking about where the river has actually been moving around, because that's going to affect where you should be implementing restoration. You don't want to be putting it in an area where the river is likely to come through and just take all that out. And color-coded here would essentially a spectrum of intensity, red down the green. Red being the most frequent areas, the most frequently scoured areas or disturbed. It's not always scoured, it's sometimes deposition. And then down the green. So the red areas where it was disturbed in all of the map floods, and then green disturbed in only about one flood. Okay. And this is a methodology that we adapted from other work that researchers have done in the Southwest, namely the Colorado and other places in Arizona. Okay, so the next step is the invasive plant map. So this is a subset of the broader vegetation mapping effort. So this is focusing just on the invasive plant mapping, getting the Arundo percent cover. The red areas are essentially the big, dense stands of Arundo compared to any sort of native representation, which is typically willow. So the red is a big, dense Arundo stand. And the yellow is a more evenly mixed stand. And then the green is mostly a native stand, typically, again, of willows. So then we put these together, because we're mapping here. We're trying to find out strategic locations. And we put these together. We have a flood reset zone, which came out of those high frequently scoured areas. And again, we're using the past to inform on the future. Where it has scoured most frequently in the past is most probable to scour again in the future. So we want to avoid that area, or at least work within those constraints appropriately. So the dense stand of Arundo, that's the red vegetation that falls outside of the reset zone, that's an area for high priority Arundo removal and revegetation. That's an area that's outside of the scour potential zone. It's not likely the river's going to do the removal work for you, and that's an area that direct removal and revegetation should occur. Conversely, within the reset zone, that's an area that the river is going to do the work for you, and you should take advantage of that and not waste time removing vegetation, Arundo, that the river is likely to help you. So that's a low priority area. Once the river does scour out those areas and remove the Arundo, and it'll remove natives as well. But that's a low priority area. But once the flood does take up and do the work for you, that's a post-flood contingency treatment area. And then the green is that dense stand of native vegetation, and that's a high priority for protection and enhancement. It's not likely to be disturbed, so you can do some active, definitely protection. We're talking about protection from landowners or land uses for preservation, and you can also do some strategic removal and replanting in them. And then this is the final product of a more detailed strategic plan of coming out with each of the different steps that can be taken and then their priorities. So this is our approach that we are in the middle of, or most kind of in various stages on the Virgin River. So speaking of the Virgin River, so let's get into it. So we're talking about the Virgin River, and this is the very large Virgin River watershed that Tom Dudley and Heather Bateman talked about yesterday. It's a big amoeba-shaped watershed. And we're not dealing with the entire watershed. We're dealing with just the main stem river. So that's about 130 miles from Zion all the way down to Lake Mead. So Utah, Arizona, and Nevada. And the issues, again, the dense tamarisk infestation, the presence of the leaf beetle co-occurring with the endangered swiffle habitat. We have our scientist blinders on. So we're ignoring what I'd call the socio-political issues, which are also inherent in this watershed. And that is, we're dealing with 3 states, multiple counties, and multiple jurisdictions of federal and state and municipal resource agencies. So we're kind of ignoring that, and that'll be dealt with later by others probably. And so again, we're just going to focus on the physical and the biological factors. So the first thing I did as a geomorphologist is, of course, I started to characterize the different parts of the river, and it's a very diverse watershed, and of course it's a diverse river system as well. We're talking about a river that comes from Zion, from the Colorado Plateau, and then enters into the basin and range. So in total, there's about 8 distinct hydrogeomorphic reaches along the river. You can further subdivide those into about 26 sub-reaches. So it's a very diverse valley canyon morphology throughout the course of the river. And the flooding, the episodic hydrology through here, which is a primary driver for what you see in the system, and of course is a primary condition that needs to be considered when doing anything, be it housing developments or flood protection. or restoration planning on the river. So this is the long-term gauge record of flood peaks taken from 5 of the longest-term stream gauges that run along the length of the river. And so we're going from 1910 to about 2010 for the longest gauge. And we want to map the actions that occurred with contemporary flooding activity. So we're in the pink circles here are the 3 most recent large floods. And so we acquired imagery taken just after each of these. We got some additional support from the Nature Conservancy in a few reaches in Utah. And so we looked a little bit deeper in time. That's 1955 and 1966. So, but for the entire river, we looked at 1989 flood effects, 2005 flood, and 2010 flood. And we have an outlier up here. This was an artificial flood from the dam breaching at Quail Creek Reservoir. But nonetheless, we're considering it because it did have an influence on the morphology of the river. So we still are going to consider it. It has a return period computed at greater than 200 years, so it's a total outlier. It's an artificial flood event, but nonetheless, it influences the geomorphic character of the river. So we're going to consider it. The 2005 flood and the 2010 flood, respectively, have about a 50 and a 40-year return period, which you'd say, well, those are very closely spaced for being only 6 years apart. Very large floods. But they're fairly representative of the large floods in the system that could happen again in 5 years, 10 years, 15 years. And it's not unusual. You could see there's other occurrences of very closely spaced large floods. So that's the kind of system that we're working with here in this free-flowing river. What does this look like? And I love this picture as a geomorphologist. This is some. I think about this. Most people run inside when it rains, and Tom Dudley ran outside and took this picture. This is in the Virgin Valley, just below the gorge. This is what 31,000 CFS looks like in the channel, and then that's what it looks like most of the time a couple months later. And you can see the freshly scoured point bars with some mostly tamarisk remaining. Okay, so we did flood scour mapping for those 3 floods for the entire length of that 130-mile long river. I can't show that to you very easily here unless I brought it into Google Earth and make people dizzy by touring around. So we're going to focus just on this example subreach here. This is in Mesquite. This is at that Hughes restoration site that the Partners in Conservation have been working on. And so we have a subreach from here to here. This is the town of Mesquite that is quickly migrating its way toward the river. And then this red box here is the parcel that the restoration group has been working within. To help us characterize that the most recent post-flood effects and other conditions as well, we worked with Utah State University, and they collected high-resolution color and multispectral imagery. They collected high-resolution topography LiDAR, and they collected, and then from the multispectral imagery, which if you're not familiar with is, it's reds and greens. It looks like false color, but it's just a different spectrum, and using the spectral signatures of the various features that it's taking photographs of, you're able to actually tease out the dominant vegetation. And Bruce is going to talk about that in his next, in the next talk. But we have most of that. Okay, so let's go through and look at some fun pictures here. So this is the same reach, photo taken in 1993, just after the '89 flood. Same exact extent, taken just after the 2005 flood. So you can see the low flow channel has moved. There's rescouring, movement of material, excavation and deposition. And you can see the school funding was built and the town is migrating its way. There's a wing dike over here that they installed, and that's what the 2010 did to it. So some very dramatic changes, and actually upstream, much larger sweeping changes. This is a fairly constrained reach. So throughout the river, especially in the valley reaches, there's dramatic changes every time there's a decent sized flow. Okay, so let's start mapping it. So we're going to categorize the degree of flood scour, and so this is looking back again at the '89 flood effects, and so the red is a color intensity. We're primarily using vegetation, remaining vegetation as an indicator. So if an area looks freshly scraped clean or deposited, so if there's a barren surface, that's going to be an area that indicates a high scour location. Okay, so red represents that area, and we're essentially using less than 10% remaining vegetation. Medium is going to be like as it's described in yellow here, so 10 to 80% remaining vegetation, and then the low is as it sounds. It's an area that does not appear to have any scour. It may have been flooded, but there was no geomorphic change through there. Okay, so here's the flood scour categories for the 2005 flood, and then the 2010 flood. Okay, and then what we're going to do is we're going to ignore the low categories. We're going to deal with just the high and the medium, and call that the active channel area. Okay, and we're going to do that for each of the floods, 89, 2005, and 2010. So in yellow we have the active channel area for 89 flood, orange the active channel area for the 2005, and active channel area for 2010 in red. So they're overlaid on top of each other. The gray is the combination of all the lows. Again, it's not a FEMA map. It's not telling you where you might lose your house or what have you, but it's just kind of leftover information. And here's their final step. We want to get to the flood reset zone. We're talking about frequency and probability. And we are going to then use the frequency of occurrence within any given location. And essentially in the red and the yellow are the areas where there's been more than one flood scour event activity. Okay. All right, so we did this for the entire river, again from Lake Mead up to Zion, and we finished this back in July and put out a little memo because the goal of this project is to disseminate this information, talk with people, get feedback, and share it with the people who are actually going to use it. Okay. So this is a little memo that we put out, and we also shared shapefiles and Google Earth files. All right, so we finished the flood reset zone mapping. We are in the process of still receiving, and we've received most of the river for vegetation. This is what Bruce will cover next, but this is coming from Utah State University. From the combination of the flood reset zone with the mixture of vegetation coverage throughout the system, we can then start to identify high priority restoration areas. Again, we're being strategic about where best to implement restoration because of the considerations of primarily flooding. Because of course, again, that example of the many sites that unfortunately had unsuccessful results, which along the entire river. So that's at the reach. That's at the river or the reach scale. Something that we'd like to do next is to zero in, and it's been mentioned during other talks as well, of the need to consider other environmental factors: soils, groundwater, salinity, and so forth, wildlife habitat. And so what I'm going to do next is start to, we're going to use the same reach, and we kind of drill down a bit more. And we didn't do this for the entire river because it wasn't part of our grant. But here's some of the site scale information or environmental factors to consider as well. And I'm going to look at the vertical changes. I'm going to share with you some vertical changes using some repeat LiDAR. And then Bruce will get into more detail on vegetation, proximity to surface water, proximity to willow flycatcher occurrence, and soils and depth of groundwater. Okay, so here's what the LiDAR looks like, at least in contour form, draped over the imagery, so you can kind of get a sense of where we're in the exact same location I was showing before. Okay, and after we started the project, we realized, wow, there's actually quite a bit of other LiDAR data out here. And so my eyes lit up, and I said, please, can I have it? And so in yellow, this is the river, and in yellow here is our 2011 LiDAR. Here's the upper river in Utah. There is a pre-2010 flood LiDAR. So we can look at the three-dimensional changes occurring with that flood. We haven't done that yet, but we can. And down here we have data that actually goes before the 2005 flood. So we can actually look at the volumetric changes in a reach, actually the whole river, but in a reach before and after the 2005 flood and before and after the 2010 flood. It's quite a unique opportunity. And so we did that for our example reach here to kind of start to drill down and look at the various changes that could influence and inform on effective restoration implementation. So this is like a big blue and red blob map. And what we've done is we're looking at the effects of the 2005 flood. So we've taken pre-flood LiDAR and post-flood LiDAR, and we've taken their elevational differences. Okay, so in blue, kind of looks like a river. It is a river. In blue is areas where the bed has dropped, okay, erosion, scour. In red are areas of deposition, buildup, okay. And you can see there's this varied change throughout, as you'd expect. And you can do a quick sediment budget. And for this subreach, there is a net loss of material. So there's greater erosion than deposition. And in this particular reach, it's not unexpected. It's fairly constrained. There's urban encroachment. Upstream and downstream, it's wider, broader. You would expect perhaps the converse. Within the restoration parcel, primarily erosion. Now we're going to look at the changes with the 2010 flood. And, sorry, I'm almost done. And this is the effects of the 2010 flood. Again, more changes. We're talking vertical changes. It's a fairly mixed occurrence of deposition and erosion within the site. Net erosion for the whole subreach. And here's the combined effect, net erosion. So this reach is cutting down. And it's losing material from these repeat flood events. You would hope that perhaps it will build up during some intervening flood years, but you'd have to measure that, or other people would have to take measurements. But overall, within the site, what's important to note here is there's been net channel lowering. So if you're thinking about planting on these surfaces here, you're going to find yourself a bit higher now than you were before from the low flow channel. And that influences rooting depth or success rate. So your restoration strategy should accommodate those conditions. Okay, so let me summarize this here so I can segue to Bruce's talk. In summary, the hydrology is a very episodic system subject to infrequent but large channel resetting events. The morphology is the channel large, broad lateral and vertical changes. And what can be taken away from this, and I'm not going to take away from Bruce's talk, I'll just focus on the physical processes, and that is at the river scale to avoid the flood reset zone and to ensure the sustainable, cost-effective strategy. And at a site scale, there's other additional factors to consider as well. The vertical changes, for example, and Bruce is going to talk about the vegetation and the wildlife elements next. So that is it, and I'll let Bruce go through the exact same acknowledgements. That's it.
We have time for one question. Oh, one in the back there. We're going to try to use the mic. It's easier.
Is it on? Is it on?
There you go.
Really fascinating work you guys have been doing. What I want to know is how a land manager is going to figure out where the flood reset zone is without doing GIS work, or if there's some easy GIS that somebody can do.
It's done. So we did this for the entire river. So it's done. So and all of this information is going to be provided. It already has been provided, and we're going to be doing technical. We've been part of several stakeholder meetings and discussions with resource agencies or the restoration groups, and we've already been sharing this information since the summer. And what we're working on and trying to wrap up quickly is that final integration of the flood scour with the vegetation conditions, so we can get to the actual high priority restoration site location. And again, we're doing that for the entire river. So if you have restoration sites or own land on the river and you want this information, it's there. No one has to recreate anything, barring another major event or something that comes along. But essentially, this is intended to be a very rich, very usable, accessible data set right now.
And for other rivers, how much work is this?
It's a pretty standard process. It's tedious, no doubt. And I had the co-authors on at the very title slide there, Carly Rodriguez, who's our GIS workhorse. There's a lot of clicking away on GIS, but there's quick and dirty approaches to a lot of things, and there can be for here as well. And if you're looking just at a particular parcel, we're looking at the 130 miles of river, but if you're looking at a particular parcel, it's not too hard nowadays to pull up Google Earth and just kind of scan through the historical images that are already available for much of the world and just see what sort of activity has occurred. Currently, there may not be, the channel may be far from your current lands, but, in 93 or in the 80s, it may have been there before. And if there's nothing to stop it, it could be there again. So there's that kind of quick information available to just look at least at the geomorphic potential of change. And then the vegetation, if you own the land, you probably already know what's out there.
Great, thanks.
Sure.